Alright, well, happy e-learning to everybody. We're going to start our next chapter today. In this first lesson of it, the first half of all these notes should be familiar to you guys already. What we're going to talk about in the first half of these notes are logarithms, natural logs, properties you could do with them, what's the point of them, expanding expressions, condensing expressions. Everything that we're going to talk about in the first half of these notes, you've already seen in pre-cal and in Algebra 2. As far as the properties go, there's not a lot you can do on top of what you've already learned. And then the second half of the notes, we're going to get into another differentiation rule. So we're going to kind of go back to first semester when we talked about all the differentiating rules, so product rule, chain rule, and we're going to learn one more way that we can differentiate. So let's refresh our memories on logs and natural logs, and what are they and what are their properties. So when you guys first learned these in Algebra 2, you learned that a log is just another operation. Just like you have multiplication, you have division, addition, subtraction, you also have log. And what a log does, it's just a way to get an exponent by itself. Before you learn logs, you never were able to solve this equation. I'm going to put this equation here. You don't have to write this. But before you learned about logs, you never had a way other than guess and check to solve this equation. Well, then we introduce logs, and it opens up your math toolbox, if you will. So if you have b to the x equals a, so this thing right here, and you want to isolate this exponent right here. Basically, if you want to get the exponent by itself, you write it in terms of logs. And if you remember, it would be log. The base of the exponent is the base of the log, so you put your b here. A log equals an exponent. So since your exponent is x, your log is going to equal x, and the result from the exponent form is called the argument of the log. It's the number inside the log. That's called an argument. By definition, a few things have to be true, and that's right here. So in log form, a and b have to be greater than 0, and also b can't be 1. And we'll talk about why here in just a second. Okay, so that's how you go from log form to exponent form and vice versa. You just have to know where those three numbers go, but you've talked about this for quite a while. Alright, so if we have log base 3 of 81 equals 4, and I want to put that into exponent form, what that means is 3 to the 4th power equals 81. 3 to the 4th power equals 81. So the base of the log is now the base in the exponent form. The 4 over here is now your exponent, and then the 81 is the result. Okay. Well, let's say we wanted to write log base 10 of x. So log base 10 of x, we can write this in another way. There are two really commonly used logs. If you see log base 10, typically you'll see just log of x without the base 10 there. And we call this the common log. That's the common log. So if you see directions that say use common logs, they're referring to log base 10. And then the other one that's really common is log base e of x. And this is where, if you remember back in pre-cal and Algebra 2, this is where ln comes in. All natural log means it's the same as every other log. It's just base e instead of base 10 or base 5 or base 100 or whatever. So that's what natural log means. And this is, again, like I just said, called natural log. Okay. So that's what a log is. That's the point of it, is to be able to get an exponent by itself. But with logs, they come with certain properties. And again, these are things that you have talked about already. So what are some things that we can do with logarithms? Well, if you have ln of 5x, if you have something being multiplied inside of the log, see how you have a 5 times an x right here? You can split this up into two different logs that are being added. So I could put ln of 5 plus ln of x. So if you have an argument of two things or three things or four things being multiplied, you could split it up into separate logs that are being added. And it goes the other way. There will be times where we want to take an expression like this and condense it into one log. So all these properties that we're going to be talking about go in the other direction as well. Well, if we have ln of 5 divided by x, we could split that up into subtraction. That would be ln of 5 minus ln of x. So if you have division inside of a log, that implies subtraction of two separate logs. One that's really powerful is if you have an exponent inside of a log. So on example 3 right here, you're allowed to take that 2 and pop it out in front and make it your multiplier. And this would be 2 ln of x. That's really powerful if you're trying to get rid of exponents. And it also works in the other direction. If you have a number in front of a log, you can put it as an exponent. A couple shortcuts. If I had ln of e, and I want to know what that equals, keep in mind what a log is requesting. So I'm going to put another example over here. Let's say I wanted to ask you guys, what is log base 4 of 64? And say this is the question that was posed. And understand what this is asking. This is essentially asking 4 to what power equals 64. This is a request for that. 4 to what power is 64? And this would equal 3. 4 to the third power equals 64. Well, jumping back to ln of e, well, remember, if you have ln, essentially there is a base e down here. We just don't put it. And this is a question of e to what power equals e. And that would just be 1. So if you have ln of e, that just equals 1. In example 5, there's an e down here. And this is a question for e to what power equals 1. And then you have to remember that anything to the 0 power equals 1. So e to the 0 would equal 1. So those are just a couple of shortcuts, things that you might see. Alright, so I said above, we had those problems where we couldn't solve them until we learned logs. And here's a case where if I have 2 to the x equals 5. Well, now we have this operation of log that we can actually solve this equation. And we're allowed to take the log of both sides. I'm going to use ln on these problems. And I'm going to rewrite this so I have some room. Oops. And now that won't erase. So anyway, let's say I had 2 to the x equals 5. I'm allowed to log both sides. And I'm, in this case, going to natural log both sides. So I can ln. So I could put ln in front of each side. And that's the same as like dividing both sides by 5, adding 2 to both sides. You're just taking the natural log of both sides. So it's just a math operation. And the reason this is helpful is because now we can take this exponent and pop it out in front. And we have x ln of 2 equals ln of 5. And now to get x isolated, we could just divide both sides by ln of 2. And so in our calculator, we'll do ln of 5 divided by ln of 2. And I already went ahead and did this, but that's 2.322. And you could take your calculator and double check that if you would like to. Okay. So let's use some properties to expand a couple expressions. Sometimes you're going to be given a problem where it's going to be beneficial to expand an expression. So we have ln of 2x over y. And if I want to expand this, first thing I need to realize is these two things are being multiplied. And then I have a division sign here. Okay, so I'm going to use a couple of these properties. So I can split this up, and I'm going to do this rather quickly since these are things that we have learned. And this would be ln of 2 plus ln of x minus ln of y. So when I want to split this up into 3 separate logs, the 2 and the x are being multiplied. So notice now those 2 logs are being added. And then there's a division, and so now that's where the subtraction comes in. So we split it up into 3 separate logs. We expanded it. Down here, if I want to expand ln of 3e squared, okay, well, I can split this up into 2 separate logs first. ln of 3 plus ln of e squared. So I split it up into 2 separate ones. When we expand, we're going to leave the ln of 3 alone. I don't know what that is without a calculator, so we're just going to leave it alone. But over on the right, we can take this 2, put it in front. So we have ln of 3 plus 2 ln of e. And we talked about above that ln of e is just 1. So we have ln of 3 plus 2 times 1, which is just 2. And this is not ln of 5. These are completely separate terms. I can't add these together. That's my final answer. So we expanded. Alright, moving on to the next page. Well, we talked about expanding. Well, let's talk about condensing. So let's say I have multiple logs, and I want to condense them into a single log. Well, we're going to do this in 2 steps. First step is we're going to take all these numbers that are in front and put them back as powers. So we're going to have ln of x cubed plus ln of y squared minus ln of z to the fourth. So when condensing, put those back as powers first. And now we want to condense all these. Well, I see addition, so that means multiply. And I see subtraction, that means divide. So I'm going to have ln of x cubed times y squared divided by z to the fourth. Notice all those operations occur in the argument, inside of the log. I'm not dividing the whole log by z to the fourth. And that's something to keep in mind. A common mistake people will make, and I'm going to write this in red, they'll do this. They'll put ln of x cubed y squared divided by z to the fourth. And that's incorrect. Or they'll say divided by ln of z to the fourth, and that's wrong also. So all your operations, when you're condensing, occur inside the argument of the log. Okay. Well, what does the graph of f of x equals ln of x look like? What's that graph look like? And some of you, I know in my Honors Algebra 2 class, we didn't really talk about the graphs of these very much. Probably in pre-cal you did a little bit more. But I think it's important to be able to recognize a log graph. There are going to be times on the AP test, especially with slope fields and things like that, it's important to know what certain graphs look like. And so I'm just going to draw this. Well, think about what the domain of this is. Think about what the domain of this is. You have ln of x. Think about what you're allowed to plug in for x. And if you go back to the original thing of the notes we talked about, remember a and b had to be greater than 0. The argument, the number inside of a log, has to be greater than 0. It can't be negative. So if I said what's the domain of this, I'm only allowed to plug numbers greater than 0 in for x. That would be the domain. And so what we're going to do when we graph this, I'm going to make a little table of values. Anytime I'm graphing something weird or that I don't know exactly what it is, I make a table. And so off to the side, I want to make a table of numbers greater than 0. And I'm probably not going to start with 1, but maybe a little smaller than that. So with the table I made, here's what I did. To see what this graph is going to look like, I plugged 0.1 in, 0.5, then 1, then 2, and then 3. And this is going to give us a really good idea of what this graph is going to look like. And I already did this in the calculator. I took ln of x, so I took ln of 0.1, and I got negative 2.303. And I put ln of 0.5 in, and I got about negative 0.6931. And ln of 1 is just 0. ln of 2 is 0.693. And then ln of 3 was 1.0986. Again, I just entered those in the calculator. And I figured that would save you guys some time if I just did that for you. So now when I graph these, I don't have to make too many dashes. Okay, so at 0.1 and then negative 2.3, that's going to be right about here. And then 0.5, negative 6.9 is going to be right about here. And then 1, 0. And then 2, and then 6.93, so just above halfway. And then 3, and just above 1. And what you see happen here, and again, you probably recognize this graph from pre-cal, hopefully. You have this smooth curve that looks like this, and it's always increasing. It just starts to slowly increase once you get farther out with your x values. And if you notice, this is going to go downward forever, because you can never get to 0. If your domain is x is greater than 0, that means you could plug in 0.01, 0.001, 0.00001, and you're going to keep going down. And so basically with logs, we have a vertical asymptote. And that vertical asymptote is the y-axis right here. But I think it's just important to recognize that graph, that log graph right there, for things that could occur on the AP test. Okay, so that was all review. But I think it's important to get the refresher. You know, some people aren't very comfortable with logs, and that's okay, and so that's why we just did that. But now let's get into the calculus, okay? And what can we do with these things? So by definition, the definition of natural log of x in terms of calculus, and you could find this stuff in your book as well. In fact, the examples we're doing are just the examples from your book. But the definition of ln of x is this. It's the integral from 1 to x of 1 over t dt. I'll give you a second to write that down. This is the definition of ln of x. It's the integral from 1 to x of 1 over t dt. And what this is going to allow us to do, it's going to allow us to add some integration techniques and some differentiation techniques that we haven't been able to do up till now. And let me show you what I mean by that. So look right down here. It says, what if we wanted to find the integral of 1 over x dx? Okay, so think about that. Let's say I wanted to integrate 1 over x dx. Forget about logs, forget about all that stuff. Just in general, using what you know, let's integrate this. So I would write this as the integral of x to the negative first dx. And then using our power rule that we know, we would add 1 to the exponent. Well, if we add 1 to negative 1, we get x to the 0. And then we would divide by 0. But if you remember, since 3rd grade, or whenever you learn this, you're not allowed to divide by 0. So in fact, this is undefined. So that power rule that we talked about, when we first talked about it, and you probably don't remember this, we said this power rule works except for when this exponent equals negative 1. When it's negative 1, it doesn't work. So we actually can't integrate this function. And what this definition with logs is going to allow us to do, it's going to allow us to integrate that function. Isn't that cool? And it's also going to allow us to differentiate as well. So I want to show that. So this definition from above allows us to differentiate and integrate, which we actually aren't doing that this lesson. This lesson we aren't going to integrate. I know the last unit was all about integration, but this lesson is not about integration. We are going to talk about differentiating with logs, okay? So let me show what we're allowed to do with this and what happens. So let's say I had, I wanted to find the derivative of ln of x, okay? Now we've never talked about that, and you might have looked on your sheet, that blue sheet I gave you guys, and you might have seen this rule, but I want to show this using the definition from above. So let's say I had the derivative of ln of x. Well, that would be the same as taking the derivative of the definition of ln of x, which we said from above is this. 1 to x, 1 over t dt. Okay, so that's all I'm doing. I'm taking the derivative of what we said the definition of ln of x is. This, right here, should look very, very familiar to you. This is, in fact, the second fundamental theorem of calculus. Do you remember those problems where when you had this x right here, you would just, and it said, what is the derivative of this integral? It's probably the easiest problems you guys have done on any calculus assignment all year, was when you just take the x and you just plug it in for that t right there, plug it in for that variable. And essentially, that's what's going to happen right here. When we take the derivative of this integral, we get the function just in terms of x. 1 over x. We're using the second fundamental theorem of calculus. When you take the derivative of an integral, you're allowed to take that x and plug it in for the variable. And so essentially, the derivative of ln of x is 1 over x. Pretty easy derivative rule, but that's where it comes from. Now, let's say you had some function inside of the natural log. Let's say it wasn't just an x. Let's say you had some polynomial in there or something weird inside of the log. And so now we're getting into some chain rule stuff. Let's say I had the derivative of ln of u. Well, from above, we just said that that would be 1 over u. But if you think about the chain rule, when, for instance, I'm going to put a little example over here. Let's say I wanted to differentiate x squared plus 1 squared. Well, we would take the 2 out in front, and I'd get 2 x squared plus 1 times the derivative of the inside, which would be 2x. So we would get 4x on the outside. You remember the chain rule. Essentially, this is the chain rule. So we would take 1 over u times the derivative of u, or u prime. So anytime you're differentiating a log, a natural log, it's going to be 1 over the thing inside the log times the derivative of the thing inside the log. In other words, it's just going to be u prime over u. And you'll see that on your blue sheet as well, that little property there. Well, let's use this. Let's use what we just learned. So basically the last 5 minutes is just developing this differentiation rule and where it comes from. But now let's use it. So we now have a thing in our toolbox that we can use. So if f of x equals ln of x squared plus 1, find f prime of x. Okay. Well, in this particular case, I'm only going to do this for this example, but I want to use the u situation from above. The u in this case is x squared plus 1. That's the thing inside the log. And then u prime would be 2x. So if I know what u prime and u are, I can differentiate this thing. That means f prime of x would equal u prime over u, which in this case would be 2x over x squared plus 1. That's our derivative right there. So you take u prime over u, the derivative of the thing inside, divided by the thing inside. Let's look at another. I forgot to say find g prime. I thought I did when I typed these up, but find g prime. So we have natural log of square root of x plus 1. Okay, so this is the same as taking natural log of x plus 1 to the 1/2. Square root is the same as the 1/2 power. I'm going to go back to black. For you OCD people, you might get bothered, but that's alright. So let's say I wanted to find, well actually now we can simplify this because we could take this exponent and also put it out in front. So we have 1/2 ln of x plus 1. So we haven't done anything with derivative yet. All we've done is clean up this function to make it a little easier to find the derivative of. So now I'm going to find g prime. G prime equals, and it's going to be 1/2 times the derivative of ln of x plus 1. And so from above, we would take the derivative of the inside. The derivative of x plus 1 is 1 over the inside, which is x plus 1. So we get 1 in the numerator, 2 times x plus 1 in the denominator. There's our derivative. So it's the derivative of the inside divided by the inside. That's our log rule. All right, last page. I copied this or scanned this a couple of times. I don't know why it turned out all grainy like this. I tried it multiple times. Must have been the paper. I have no idea. Anyway, so if g of x equals x cubed times ln of x cubed minus 5, find g prime. And we look at this, and this looks a little messier. And hopefully you recognize, because we do need to go back to first semester thinking now, in terms of finding the derivative, we have a product rule right here. We have x cubed right here being multiplied by this thing, ln of x cubed minus 5. We have product rule. So we have to remember how to use the product rule. The product rule says take the first function times the derivative of the second plus the second function times the derivative of the first. Well, let's do it. So g prime equals, we'll do the first times the derivative of the second. So the second one being this function right here. So if I want to find the derivative of this, we take the derivative of the inside, so 3x squared, divided by the inside. Right there. Plus, now we take the derivative of the first one, that's the x cubed, the derivative of x cubed is 3x squared, times the second one, ln of x cubed minus 5. There's our product rule. Now let's just clean this up just a little bit. So in the first fraction we're going to have 3x to the 5th over x cubed minus 5 plus, well, we can't really do anything with this. We'll just put 3x squared ln of x cubed minus 5. There you go. I mean, if you're sitting there doing this, you might say, well, we could get common denominators and add these together. And yeah, you could. That's another way you can add these things together. But for now, we're just going to leave this right here. There's our derivative. All right. So now we get to this one. And this one gets rather messy. We only have 2 examples left, so keep your focus right here for the last 2 examples because they're pretty important ones. It says, use logarithmic differentiation to differentiate y equals this messy thing right here. So when functions are really messy or really difficult to differentiate, we can use logs in order to clean things up and then use our log differentiation rules instead. And even in doing so, this is still a pretty messy example, just to forewarn you. But it is a way that we can differentiate this mess of a function using logs. Okay, so I'm going to rewrite this function right over here. I'm going to have y equals, and instead of putting cube root, I'm going to put x squared plus 1 over x squared minus 1 to the 1/3 power. Remember, when you're taking the cube root, that's the same as 1/3 power. And the next thing I'm going to do is I'm going to take the natural log of both sides. So I'm going to take the natural log of the left and the natural log of the right. Okay. Now what I'm going to do is take the derivative of both sides, because now we're going to use our log differentiation rules. So I'm going to take the derivative of the left side and the derivative of the right. Now, on the right side, we can actually, the reason we use this is because we can take this thing right here, this whole thing right here, and using log properties, we can actually expand this thing out and give us some easier expressions to work with. So I'm going to expand this out. I'm going to have 1/3 ln of x squared plus 1 minus 1/3 ln x squared minus 1. Let me explain where this came from. Essentially, I took this 1/3 and I put it out in front of each of these. So that 1/3 is essentially in front of both logs. And I took this quotient inside the log and I split it up into subtraction. And what this is going to allow us to do is now we're going to be able to differentiate these individual logs using the differentiation rules we just talked about, which aren't very difficult to use. So that's what we're going to do now. So the derivative of ln of y, now it's with respect to x. So if you remember implicit differentiation from first semester, remember where we would differentiate and you had x's and y's in the equation, and anytime you differentiate an x term, you do it as normal, but anytime you differentiate a y term, you then have to put dy dx behind it, since you're saying it's with respect to x. That's what we have to do here. So the derivative of ln of y is 1 over y dy dx, because we have to specify that that's the derivative with respect to x. Over on the other side, we're going to have, well, we just differentiate this thing first. So we're going to have 1/3, the derivative of the inside, and actually I'm going to pull that 1/3 out. So I'm just going to take the derivative of each log. So I'm going to have the derivative of the inside, 2x, over x squared plus 1, minus, let's differentiate the other one, 2x over x squared minus 1. And this is just using the log differentiation rules that we just talked about right here. So already it looks a little cleaner. What I want to do next is, I'm going to run out of room here, I think, too. So I have 1 over y dy dx equals 1/3, and I'm going to combine these fractions on the right side, which means I'm going to multiply the first fraction by x squared minus 1 and the second fraction by x squared plus 1. I'm trying to get common denominators here. So I would multiply actually top and bottom by both. So I'd get minus 1 here, and over here x squared plus 1. I'm going to get common denominators. And so when I do that, I'm going to get 2x times x squared minus 1 minus 2x x squared plus 1 over x squared plus 1 x squared minus 1. All I'm doing in this step, and this step looks messy, but all I'm doing is getting common denominators from above to be able to combine those fractions. That's all that is right there. And so I'm going to distribute the 2x here and here, and the 2x here and here. And so I get 1 over y dy dx equals 1/3 2x cubed minus 2x. Over here I'm going to get minus 2x cubed minus 2x over x squared plus 1, x squared minus 1. And then you notice that the 2x cubed and 2x cubed cancel up here. That's nice. Alright, so I get 1 over y dy dx equals 1/3 in here, combine the negative 2x, you get negative 4x over x squared plus 1, x squared minus 1. And then at this point, keep in mind what we're trying to find. What we're trying to find here is y prime, or the derivative of y. And so on the left side, you notice you have dy dx, and you have this 1 over y. Well, at this step here, I want to multiply both sides by y to get rid of that. I want to get dy dx alone. So I'm going to multiply both sides by y. Okay, and now I'm going to move this up over in this area. Okay. When you multiply both sides by y, that creates a sucky situation because now you have x's and y's on the right side. Until you remember, well, we know what y is. That's from the original problem. So we can actually replace y with what it actually equals at the very beginning. So we're going to do that. So we have dy dx. It's almost done. Dy dx equals negative 4x over 3, there's the 1/3, so I'm just going to put 3 in the denominator, x squared plus 1, x squared minus 1, times y, which we know y to be this function right up here. So we're going to put that where the y was from the previous step. I'm going to write this a little bit different, though. I'm going to split that cube root up to the numerator and denominator and put x squared plus 1 to the 1/3 over x squared minus 1 to the 1/3. Then we're just going to clean up using some exponent rules, and we get dy dx equals negative 4x. Now if you notice, you have x squared plus 1 here, x squared plus 1 here. Using some exponent rules, the same base, and you're dividing, well, if I have x squared plus 1 to the first and x squared plus 1 to the 1/3, that means I'm going to have on bottom x squared plus 1 to the 2/3. You just subtract those powers. And then I can combine these ones on bottom. I can combine x squared minus 1 to the first and to the 1/3, and that would be 4/3 when I add those, since they're both on bottom. X squared minus 1 to the 4/3. Okay, this was using logs to differentiate. Keep in mind what the whole idea was. And you know what? This problem might have been easier to use chain rule, quotient rule, mixture. It may have been. I didn't try it. It might have been easier. But the idea of this whole thing, let me re-explain that, because that looks like a big jumbled up mess. I get that. But the whole idea is if you're given a very messy function, and like I said, we could use chain rule, quotient rule, but here's just another way using log properties. You could take the natural log of both sides, and what that does, that lets you split up that original function. That's what this whole point was right here. It lets you take that original function, split everything up, and then use your log properties. And it probably wouldn't be so bad if we didn't have to do a whole lot of manipulation and combining these fractions and things like that. That kind of got in the way of the point of the problem. But that's the idea, is you take the natural log of both sides and then differentiate using those log properties. So I think there's 1 or 2 on your assignment where you'll have to do something like that. And it says in the directions. All right, last one. This one's not so bad. Find any local or relative extrema. I wanted to stress this. First semester, I said relative a whole bunch. Find any relative minimums, relative maximums. From watching videos now and learning more about the AP test, for whatever reason, the AP test is now starting to go more towards the word local. So you might see local min, local max, and I addressed that first semester, but I just wanted to say that here as well. So find any local or relative extrema for the function y equals ln of x squared plus 2x plus 3. And think about what we're trying to find. We did a whole bunch of these problems. When you're looking for relative or local max and mins, you want to find out critical numbers. The first thing you want to find is critical numbers. And that's where the derivative either equals 0 or undefined. And then you do your number line. And you look for where it's positive or negative and where it's changing. Just to give you an idea of how to enter the problem. So if we want to find where the derivative is 0 or undefined, we first have to find the derivative. So we have y prime equals, it's just a natural log function right here, and our natural log rule says take the derivative of the inside, so 2x plus 2, over the inside. So to find the derivative of a natural log is actually really easy. And then what we want to find is our critical numbers. And remember, that's where the derivative equals 0 or undefined. So I want to find out where this equals 0 or undefined. So it's going to equal 0 where the numerator equals 0. So if I want to find where the numerator equals 0, set it equal to 0. 2x equals negative 2. So x equals negative 1 is a critical number. That's a number we have to test and see if the function's changing from, or the derivative's changing from positive to negative. And then we want to find where it's undefined. It's undefined where the denominator equals 0. Well, this sucks because it doesn't factor, so we can use the quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And we get negative 2 plus or minus the square root of 4 minus 12, which is negative 8. Now, we'd be able to simplify this using imaginary numbers, but essentially what this means is that there is no real number where this function is undefined, where this derivative is undefined. So that whole thing we just did was irrelevant. We didn't know that, but that makes that irrelevant. What that means is the only thing we need to test is this value right here on our number line. So let's do that. Remember what we're looking for. We're trying to find where the derivative is changing from negative to positive or positive to negative. So we set up our number line. And we have y prime. We have negative 1 right here. And we want to see what's going on the left of negative 1 and on the right of negative 1. So if I put negative 1 into the derivative, well, I have two parts to the derivative. I have 2x plus 2. And I have x squared plus 2x plus 3. So what I want to do, instead of trying to keep all this stuff straight in my head, just figure out what each part becomes, and then I know what a positive divided by positive is, I know what a positive divided by negative is, and so on. So let's say I plug 0 in, because remember, we want to plug numbers left of negative 1, sorry, I messed that up. Let's say I plug negative 2 in, because I want to test to the left. So if I plug negative 2 in, this top thing here is going to be negative, and the bottom one, let's see, negative 2 squared is 4, minus 4 is 0, plus 3 is positive. And a negative divided by positive is negative. Remember what this means. This means if your derivative is negative, that your original function is decreasing. And then let's test 0. So if I put 0 in, I get a positive and a positive, which is a positive. And if your derivative is positive, that means your original function is increasing. So since it's changing from negative to positive, at negative 1, we have a local min or relative min. So we'll say local, just because I didn't use that word very much, local min at x equals negative 1. And a justification, remember, you're going to have to justify in the AP test. Our justification is real short and sweet. We say because y prime changes from negative to positive at x equals negative 1. You'll have to use that justification, no doubt, on your AP test. All right, I know that was a lot. First half of the notes was reviewing log properties. Second half was just developing the how to differentiate a log, natural log, and then essentially using it. And then in this chapter, we'll also get into integrating as well. So, good luck on your homework. Peace out.